Hello everyone, and welcome to AASC's webinar series, Introduction to Steel Bridge Design. This is session L4, Fatigue and Fracture Design, presented by Robert Connor. Today is November 2nd, 2017. My name is Christina Harbour, and I am with the AASC Continuing Education Group, and I'll be moderating today's presentation. I want to introduce today's speaker. Dr. Robert Connor has over 20 years of experience in the research and field testing of bridges and related structures. He's currently a professor in the School of Civil Engineering at Purdue University and is the director of the Steel Bridge Research Inspection Training and Engineering Center at Purdue University. Over his career, Dr. Connor has conducted field evaluations of bridges throughout the United States and has participated in bridge evaluations internationally to identify the causes of fatigue cracking, brittle fractures, and to develop effective retrofit strategies. He's currently leading efforts in the United States to reevaluate the concept of fracture critical members and to develop and integrate a fracture control plan applicable to both highway and railroad bridges. Welcome, Rob, and I'll let you take it from here.
All right. Well, thank you, Christina. Welcome, everyone, today. I appreciate the opportunity to chat with you a bit for a little bit of time about the limit state of fatigue and fracture as it relates to, we're going to focus on highway bridges today, but many of the concepts are extendable to railroad bridges, of course. So as we move forward, a couple of the things we need to first kind of get an understanding of is our learning objectives today. And as Christina kind of talked about some of these, we'll focus on a big difference between fatigue and fracture itself, nominal stress, how we treat fatigue in this country, how we look at it from a bridge design point of view, an evaluation point of view, and the big influences of the details themselves, and as well as residual stresses, as well as how AASHTO treats this. And then we'll close up with a little bit of discussion about this idea of fracture critical members and where we're headed in that. So the first question is, what is fatigue? And many of you, hopefully you're not bored already with this presentation, but if you sit and you have a piece of paper clip when you're kind of bored and you keep bending it back and forth, eventually you end up with two pieces of paper clip. And that's really fatigue. It's a process, it's a mechanical process where we begin to damage the material, so to speak, usually at locations of high stress, and these defects grow by cyclic loading. So it's a lot different than strength. In strength design, as it was already covered, that's kind of a one-time event. Fatigue is different, right? This is the day-to-day vehicles crossing a structure. And it was talked about earlier in the sessions, but there is a specific load that we use for fatigue design. And in that load, the way it was developed, we don't include the effects of cars or light pickup trucks. And simply that's because they don't contribute to stress ranges that would cause fatigue damage. In other words, they're very light. It's really trucks that are the damage we worry about. Now in some courses people will say, well, the member loses capacity. And they kind of stop there. And while that's a true statement, we want to make sure it's clear that the steel doesn't change. It's not losing capacity because it's changing in strength. If you had a grade 50 steel, a 50 KSI yield strength steel at the beginning, and then you put 10 million cycles, well, you'd still have that steel, but it's kind of like you're slowly saw cutting the steel, and that's because of the crack growth. So you lose strength because of loss of section. And another important point, and we'll see some of these numbers, is that the stress ranges, the cyclic stresses, don't have to be all that large to cause damage. And that's particularly true where you have a category, and we'll talk about what I mean by that, but a classification of a fatigue detail that isn't very good in fatigue. We'll see some are better than others. Or if I already have a crack present. And then, of course, when I have a crack present, cracking can just continue at very low stress ranges. Now, we'll throw the term, and you'll hear the term about fatigue life. And it's one that has some information that kind of has to be thought about. It's really the time when we think no significant cracking would be expected. Now, always the question is, well, what is significant? Well, really, it's more important to maybe think of it as that any damage that could have occurred is insignificant, that there's no damage that we would need to worry about as structural engineers. How do we determine that then? Well, it's a little tricky. You can imagine that the way we get fatigue life data is actually from large-scale or full-scale fatigue tests. Right here at Purdue, we're running several right now. And those tests run 24 hours a day, 7 days a week, cycling girders or details. But eventually we have to say, enough. The girder failed. So is that when I can first find a tiny crack, or is that when the girder's laying on the ground? Well, generally some criteria are often put in place that, well, a crack is a certain length, or I've lost enough material to change stiffness. It doesn't necessarily mean, though, that the member is broken, and that's an important point. Now, the way we measure fatigue life is simply in the number of cycles we apply. In other words, 10 million cycles at a certain stress range. And as engineers, we don't really like to think in terms of cycles. We generally like to think in terms of life, in terms of years. If I told you 15 million cycles of life, well, that doesn't do you good. But if I told you 15 years that corresponded to, well, then that's something you can react to. Now we'll see. We'll get some plots of curves here in a little bit that will help clarify some of this. But when we talk about fatigue, there's two regions of fatigue life that we need to worry about. The first one is the easiest one, and this is the infinite life region of a detail. And basically this says that it's not likely at all that fatigue cracking would occur at that stress range. So if I go back to the paperclip illustration, and you bend the paperclip just a little bit, millions of times you might find that it never cracks. And that's what we're talking about here, that it has infinite life, infinite number of cycles at that stress range. And that's referred to as the constant amplitude fatigue limit or the constant amplitude fatigue threshold. The other region, though, that we worry more about generally is the finite life. And this is the portion of the life curve where, yes, cracking could be expected. And we'll talk a little bit more about what this means in terms of the likelihood of cracking. Fatigue is looked at statistically. The reason is we'll see there's a lot of variability in the data. If I have 10 identical tests, I can have 10 completely, well, I shouldn't say completely different answers, but a lot of variability in the life. Same specimen, same stress range, but a lot of different life. And that's because of the things that are in a specimen that are hard to quantify or in real components. And we quantify that based on the stress range that I'm applying, 5 KSI, 10 KSI, whatever, and then how long the test runs. And we'll talk more about that. So this is our common fatigue curve. A couple of things to look at here. Our vertical axis is stress range. Our horizontal axis is number of cycles. Now that's that infinite life region, the constant amplitude fatigue limit I discussed. And basically it says if my stress ranges are below, down in this region, I would never intersect a curve with time, right? This is cycles, so that's kind of like time. And I could expect to have infinite life. That's a good place to be. But the finite life curve is the other one. And so what that says is once I get above that stress range, I simply would come in, and where I intersect that curve, I can then come down and calculate the number of cycles that the detail would be expected to last. And that curve is based on a probability of cracking of only 2.5%. In other words, there's a 97.5% probability that cracking would not be expected. So it's actually quite conservative. And the way it's developed, I'll show in a second, based on fatigue test data. The curve is quite simple. It's just a number of cycles is equal to the detail constant, and all the details have different constants, and we'll see what that means in a minute, divided by the stress range raised to the cubed. But you'll notice something here on this plot, that it's log scale. So that means it's not linear. Although it shows up linear on log, right? If we plotted this linear, this would be curved. This is a very important point. What this says is you can imagine if I had some constant and I have my stress range, the life is very sensitive to the stress range, in fact, cubed. So that means if I double the stress range, if I take a stress range value and I double it, my life, n, decreases by a factor of 8. So it's very sensitive to stress range. So if I want to think about life of a bridge Well, this is the region that I'm worried about. And what happens then simply with time is if I think my bridge is brand new at some point in time, I have no cycles, but I have a certain stress range value, just simply put, as time marches on, I begin to use fatigue life until I reach the point where I say the bridge has intersected the safe life curve and I don't have any more safe life. But remember, that curve is statistically based, which means there's a 97.5% probability that it would not crack. But that's what we use for design. And of course, in older structures that have been out for a long time with stresses, sometimes we would then actually calculate a negative fatigue life. But again, that's with respect to a safe life. So although it's still standing, it obviously truly isn't negative. It just simply means that we're using up some of the safety margin, if you will, on the structure. And so there's all of these different details. I'd use the detail category and detail constant term. And really, this is the same curve, right? It's stress range, number of cycles, except now we see a whole series of curves. But they're basically the same. I have a sloping portion, and I have a constant amplitude portion. And so for category A, which is our best detail, this fatigue limit is 24 KSI. And that says for that kind of detail, if I keep the stress range below that value, I would not expect to have cracking. But I also have some details that are very poor, such as the E prime detail. And this corresponds to about a 2.6 stress range, or a stress range of about 2.6. That means that I would need to keep my stress ranges below 2.6 KSI to ensure I don't have any cracking. So that's quite low. So that, comparing it to E and A, it's almost an order of magnitude, isn't it? 2.6 times 10 would be 26, so it's very close to an order of magnitude. So quite a bit of range of different details. Obviously, as designers, we want to be up in the B and C details. Category A is base metal. Basically, that's the steel as it comes from the mill. And so that kind of steel, we always drill holes, we weld to it, we put bolts in it, maybe older structures are riveted. So it's very difficult not to have a steel bridge that has only base metal. But generally, the category B and C details are where we want to try to be. Now, this is just a plot to illustrate the issue of what I was saying about the probability of survival. This is the category C curve, finite life portion and infinite life portion, and this is real fatigue test data of certain kinds of stiffeners. And what you see is a lot of scatter, and remember, this is a log plot. So for a given stress range, if I come in and I see a whole series of dots and triangles and whatnot, all this different data combined is on the same horizontal line here. Well, that's because they were at the same stress range. But notice the variability in the life, right? From less than 1 million cycles to almost 2 million cycles. So it's not uncommon to have an order of magnitude scatter in fatigue data. So that's why we look at it statistically. So if I looked at the mean, for example, if I just took that approach, well, I would find I have lots of data that's below the mean. Well, that wouldn't be safe. And so the approach that's used in AASHTO is to use what's called the safe life, where we have the mean minus 2 standard deviation. And basically that captures 95% of the data would be between the lower limit and 2 standard deviations above that, or a 2.5% probability that you would not meet the curve, because 2.5% of the data exceeds the upper limit. So what about loading? That's kind of resistance, but what about the loading? Well, the things we worry about is the load itself. How big is the stress range it produced? That's the stress range. But it's also time dependent. So how often does this happen? And again, as we said earlier, it's really the average daily truck traffic that we worry about. Cars and light trucks, they really don't cause damage. And you can imagine there's lots of different trucks in different positions on bridges, and that then creates a spectrum, or a load range or stress range spectrum, and that's what we need to then deal with. So how do we determine these things, the stress range and number of cycles applied? Well, in our fatigue tests, and if it was a perfect world, all of our cycles would look like this, nice sinusoids, everything repeating regularly. And in this case, it's quite easy to see that my minimum stress and my maximum stress, peak to peak, well, that's a stress range cycle, in this case 9 KSI. And one cycle repeats as a sinusoid. Unfortunately, that isn't what we have in reality. As you know, trucks weigh different. They have different positions. There's multiple trucks. And this is real fatigue data. This is real instrumentation data from a bridge, where sometimes the detail goes into compression, or the strain gauge measures compression, then tension, and bigger and smaller. And, gee, what is the stress range here? Well, that's a little tricky to figure out. We're not going to get into how you would calculate this. But what we use is a concept called Miner's rule. And all that simply does is it allows us to take a variable amplitude spectrum. In other words, I have so many percent of my spectrum of a certain stress range, another percentage that's of a different stress range, and so forth. And that's difficult to use because my fatigue test was constant amplitude. I ran it at the same stress range. Well, what we do is we take this and convert it to an equivalent fatigue stress range. You can sort of think of it like an average, or a root mean square, or what we use is a root mean cube in fatigue. Seems to give very good agreement. What that allows us to do now is have the same total number of cycles. So if there was 1,000 cycles in all of this, this says if I had 1,000 cycles of 4.7 KSI, I would get the same equivalent fatigue damage as the variable amplitude spectrum. And that allows me to compare very nicely to those simple fatigue curves. So it's a nice approach because it makes life very easy for us as designers or doing evaluation. Now the categories themselves, we have several, A through E prime. We already talked about those two, where A is the best, which is base metal, no welding, no bolting, no crazy cuts in the steel. E prime is the worst. Now what's nice with the details, and this was all put together by a gentleman named John Fisher over at Lehigh University, who really changed how fatigue was looked at in this country, really in the world. And the categories account for all the things that are difficult to account for numerically. And they're based on large and full-scale tests. So for example, weld discontinuities. Now we make good quality welds. You already had sessions on fabrication. But in every weld, there's small, tiny little imperfections. You could never figure that out in a finite element model. You could assume things, but it's a random problem. The local stress concentrations at a weld toe, for example, that all varies along a weld toe, and that all affects fatigue. It's very difficult to quantify. And another very important one are residual stresses. In this case for us, generally it's when a weld cools, and we have very high stresses locked into the structure. There's nothing wrong with those, but they have a big influence on fatigue life. These three are very difficult to quantify, if not impossible to quantify numerically. Fortunately, the detail category, since it's based on large-scale test data or full-scale test data, incorporates all these explicitly. So if I do enough tests, I have all this included in my fatigue curve, and that's what we have today. One of the things when we're trying to map out a detail, what detail do I use when I have a certain design or I'm looking at a picture of something, there's usually a link between the mode of cracking, in other words, how does the crack appear or where does it appear, and that stress concentration that I was talking about that's difficult to quantify. So for example, one of the very common details, and a good fatigue detail, is something called category C. And it's referred to as a transverse connection, which should be down here, which my stress range is running this way. So I'd be worried about that weld right there at the bottom of the stiffener. But it also applies to this butt weld, where the grounding, the reinforcement was not removed. So these welds are full penetration welds. My stress is also running this way. And if you just take first glance, they don't really look like anything like each other, right? I have a plate and a T coming off of it in a way, but they're actually very similar. The stress in this plate is slightly interrupted because there's an attachment, this little weld that's on here. The stress coming this way is interrupted slightly because of this little reinforcement that's left. And they would be both susceptible to what's called weld toe cracking, right at the end of the weld here, or this end, or the back side of that weld. And that's because their stress concentrations are similar. That's built into the fatigue category because of the testing. Other things related to stress that are difficult to quantify, especially years ago, is attachment length effects. We'll talk about that. If you can think of stress like water, that's a very good thing. What this is a simple little finite element model of a plate subjected to tension in the direction I'm moving my arrow, with a little attachment sticking out perpendicular to it. Same exact plate, same exact load, but now I've just made the attachment longer. And if you think about it, I can get a little bit of stress into this plate. It's not fully effective, but the longer I make the plate, well, then it becomes more able to carry stress. That's a shear lag effect. And so if I take and put some contours on here, what do I see? Well, I actually see that effect. Notice the change in color, right? I only get green, if you think of that as some stress value. It only goes in one element. Where on the longer attachment, I get in 3.5 elements almost. In other words, this plate is becoming effective. But the big issue is where we see the red locations, right? In FE, red is always bad, we think. So what do I have here? Well, I have very high stress concentrations at the end of the attachment in contrast to the short attachment. And so as we look at fatigue details, the length of the attachment is what's important, and the terminations of the attachment. Along the length, the stress just flows pretty smooth. But at the ends, what has to happen, either on this end or this end? Well, it has to come in, so there's kind of turbulence, if you think of it like water, flows smoothly, and then has to come out. And so our stress concentrations often are at the ends of details or terminations of details. So that's kind of a very quick review of fatigue before we get into the specifications. We have to differentiate fatigue, though, from brittle fracture. Very often we say fatigue and fracture. They go together like bread and butter, but they're completely different failure modes. And one of the words we always try to call folks' attention to is this word catastrophic. It is a sudden failure that occurs without any plastic deformation. That's a fancy way of saying there's no warning. Plastic deformation is what gives you warning, right? In other classes you've had in steel, when you get yielding or distortion, that's a good thing as compared to something that just breaks suddenly. In the photo here, this is one of the Liberty ships from many, many years ago that would fracture in the harbor. And in an instant, the ship was one piece. The next instant, it was in two pieces. A fracture basically broke the ship in half. Some things to keep in mind about brittle fracture, which is much different than fatigue, right? We test for fatigue and run tests for months at a time, getting cracks to grow. Brittle fracture is not like that. Applied stresses also can be low. They don't have to be high. But note this. Look how fast the crack actually runs through the material, right? Much faster than the speed of sound. Little or no shear. That just simply means there's no ductility. There's no shear lips on the specimen. In fact, when you look at the fracture surfaces, they actually appear flat, as if someone cut them with a saw at times. But the texture is quite rough. And this is a major one to take away. If the detail is susceptible to fracture, if it's put together in a way that it would potentially just break, you cannot perform in-service inspections because it could break suddenly 5 seconds after you leave. You either accept the risk it could happen, or you do something ahead of time to prevent that from ever happening. The term fracture mechanics, the branch of study called fracture mechanics, is often referred to as something you may have heard of. And what is it? It's one that a lot of times we get scared of for certain reasons, but really it's just a way to consider the effect of cracks or defects or notches in a solid. Think of it like any other limit state. So you already do strength calculations or deflection checks or buckling calculations. That's to check strength for some load combination and some failure mode. Well, fracture mechanics is looking at how much of a crack can the material tolerate. Now we perform tests for fracture. This is a plate we've tested here at Purdue, and it would have a crack built into it. That's what that little line is right there. And I wish we could show a video because they're very fun tests to see, very explosive. But what we would do is we would fatigue crack the specimen. So now we have a true crack, and then load this in tension. And this is a big test using an axial testing machine. This is a further view of that specimen. And in this case, the specimen was loaded to about 1,000,000 pounds when it suddenly then failed in fracture. And once it fractures, we look at the surface and we see some very characteristic crack surfaces. This first region here is the fatigue crack that we introduced into the specimen. Although it's somewhat rough, it's nowhere near as rough as the brittle fracture. This is the part that occurred at multiple times the speed of sound. This may have taken us a week to crack. There's another characteristic on the surface, and if you look kind of close with the shading, you see what are called, we've highlighted them here with these arrows, called chevrons. And they actually point back, if you kind of trace them, to where the fracture initiated. Now these are wonderful because for someone like me who goes out and looks at a failure, I can point back to where it initiated and people think I'm smart, but really the crack points back to where it initiated, so I shouldn't take credit for that. But they're very characteristic of sudden brittle fracture, this pattern of chevrons, and by holding a flashlight on certain angles you can reveal those. So we talked about likelihood of fatigue. Well, what about likelihood of fracture? Well, there's one term here that we didn't talk about in fatigue, and that's the material itself, and it's specifically the material toughness, or its ability to tolerate cracks. That's basically, is it brittle or is it a ductile material? The applied stress that's in the material, including residual stresses, and for fracture mechanics or cracking to occur, sudden brittle fracture, you generally need, or you have to have some kind of a defect, whether it's a crack or something that's just like a crack. Now the material itself, its toughness, unfortunately also is influenced by a number of things. One of the big ones is temperature. And you can illustrate this with a piece of gum. If you had it in your pocket all day, it's quite ductile. If you put it in the freezer, it becomes brittle. Well, steel, especially older steels, can be susceptible to that at low temperature, they become more brittle. But temperature influences toughness. How fast we load the specimen influences the toughness. And of course, the steel itself, the alloy, the process, how it's composed, and so forth. If we look at ductile versus brittle fracture, of course we don't want brittle fracture, that's the sudden failure. We would much more prefer ductile fracture, and you've probably seen slides or pictures like this before, the classic cup cone shear ductile failure versus the almost looks like it's saw cut brittle fracture. And that's the difference. If we have to pick one kind of fracture, ductile certainly is the one we would want. This is a photograph of a brittle fracture from a number of years ago from a bridge up in Wisconsin. This plate girder is about 11 feet deep, and this fractured suddenly and took out the girder. In fact, it's such a violent fracture, if you look close, you can see the compression flange is even broken. But note the bottom flange almost looks like it was saw cut, and that's the nature of a brittle fracture, very, very perpendicular to the stress. So how do we measure this property of fracture toughness? Well, we can directly measure it. And there's two tests that are quite common. One is called the compact tension test, or the single edge bend test. And these directly measure the property of fracture toughness. They're quite expensive tests, as you can imagine. You need a decent amount of material, and you need a fatigue crack in the material. You need that true crack to then measure the resistance to the crack. An indirect and certainly more common way is with the Charpy impact test, and many of you have probably seen this test. This does not measure fracture toughness directly. It actually measures energy absorption, and then we convert it back. We infer the toughness from that test. And the Charpy specimen is quite small. It's 10 millimeters by 10 millimeters square and about 50 millimeters long, and it has a little machined notch that we then hit the specimen with a hammer in a pendulum type arrangement, and then test it at different temperatures to infer what the toughness is. And what happens when we do those kinds of tests is we measure the energy, whether we're in joules and Celsius, or if we're using foot-pounds and Fahrenheit. But we see some interesting things here. At lower temperatures, I have less energy absorption. And as I begin to warm the specimen, I begin to be able to absorb more energy. In other words, the material is getting tougher. And this same type of curve actually matches what we would see for a true toughness curve. There's two regions here that are important. First is the lower shelf. What this kind of says is no matter how much colder I get, the steel really doesn't get any more brittle. It's as bad as it can get. But the same is true on this end, that even if I keep heating, eventually I can't get any more toughness out of the material. And of course, then there's a transition region. What's interesting here is this is kind of representative of some of the typical HPS grades that are routinely produced today. And I know you may not have context of toughness values, for given temperatures. But I can tell you, zone 3 for bridges is minus 60 degrees, and around here, this is very good toughness for bridge steels to have. And it's routinely produced today by the mills. So we have much better steels than we had many years ago. So this is a good slide, slide number 55 here. It's a good summary slide of fatigue versus fracture. Like we said, we test for fatigue, millions and millions of cycles. If I stop a fatigue test, the crack never grows anymore. The crack is independent of the material. AASHTO, we don't recognize in AASHTO different material strengths for the most part because of the effects of all those other things I mentioned, residual stresses and weld discontinuities and so forth. That really drives fatigue resistance. When we do inspection in the field, we're looking for fatigue cracks, and we calculate fatigue lives. Fracture, on the other hand, is a bit different, right? It is not slow and stable. It's sudden, explosive is a way to think of it. The material greatly influences. And remember, the material is influenced by temperature. So we have to consider the material that we have. Now, I say if the live load is removed, fracture can still occur. Fatigue is driven by live load, trucks, not dead load. How can fracture still occur if I got rid of live load? Well, it's quite simple. Dead load is still present. And if the temperature dropped in the presence of a crack, I could, theoretically, have a fracture occur because the toughness dropped as the temperature dropped, and the crack that was stable in August is no longer stable. We don't inspect to prevent fracture. Generally, fractures, frankly, are found after they happen. So we have to do something about them if we think we're susceptible. And fracture is kind of indirectly addressed in the AASHTO LRFD through the material we select, how we fabricate, welding consumables. But it's very important we don't do any calculations related to the fracture limit state. We handle it through, again, material detailing and so forth. I'd mentioned material, or the effects of geometry and residual stress. And these are very important, especially geometry, because it gives us insight into the likelihood of cracking. And I guess if I could, illustrate it one way that would help explain things. If you can think of stress flow like water flow, you've got fatigue, you're way ahead. You can understand a lot with how water flows. And if you, just in this illustration, if I have a nice simple water flowing through a stream and I go and put a pier in the middle of it, well, you may have heard of scour, right, that occurs. That's because the velocity of the water speeds up here. Well, think of that like stress. If the stress is flowing nice and smooth, and we'll illustrate that maybe in a plate with no discontinuities, the stress flows nice like the water. But if I come in and I introduce something, say a notch or a crack or whatever it might be, well, that stress, or water, has to get around that, right? It can't jump through the air. And as it passes through, I get turbulence, or what we would call a stress concentration. And that interrupts the stress flow. And it changes, as you can imagine. If I have something very sharp, like in the previous slide, well, how that affects the flow is different than if I have something smooth, maybe like a hole at a termination or something. So I can kind of control how I have the water flow. And it's the same thing with any other fluid flow, right? The front of an airplane isn't square because we want to have smooth airflow. Or piers are often rounded so that we have smooth water flow. Well, it's the same thing with steel. If we can keep stress flow smooth, we've helped tremendously. So let's look at this from a detail point of view. Maybe I have a plate with some stress applied in the direction I'm moving my arrow, and I have an attachment just welded on, maybe with just fillet welds. As I apply stress, although I don't design any of the stress, or I don't do anything to ensure the stress gets into the attachment, the stress doesn't know that. The stress didn't get the memo from the engineer about not entering into the element that was welded to it. So it enters into that component. And as you can imagine, at the terminations then, I'm going to have some stress concentrations in these locations because of the stress simply going in and out at the terminations. Along the length, it's actually quite smooth. Another way to look at this is if we were to even put strain gauges on an element, and we can plot the stresses as we lead up to a weld toe. we see very high local stresses occur right in these regions. And that means, of course, you can imagine that's where you would expect cracking, at the weld toe. So if I go back to that illustration from previously, and I apply my loads to my finite element model, where do we see the high stresses? Well, again, recall back at the terminations, because this is where the turbulence is. That's where the hot spot is. Now, I did say earlier that like in the front of an aircraft or at the front of a pier, we would round this maybe. Well, let's see what happens if I do that in the finite element model. If I take a simple same type illustration and I take a nice smooth radius on one end, but a sharp, abrupt termination on the other end, let's see what the difference is. I can tell you that in the AASHTO category, if I put a smooth radius here, I can improve my fatigue up to category B. Remember, they were A through E. B is a very good category. But if I leave it square and blunt, it's actually one of the poorer fatigue categories, E or E prime. Now we'll zoom in on these two ends and kind of see that a little bit better. Notice, again, if we just take the simple approach, red is bad, and all my contour scales are the same, I can clearly see that in my base material here, I have very high local stress ranges. Well, I would be expected to have a fatigue crack. But if I smooth that out and put a nice round radius, well, I get rid of those high stresses, and I don't expect fatigue cracking to occur as likely for a given stress range at this location. And in fact, I could maybe even have infinite life with the higher fatigue resistant detail. So geometry plays a major role in fatigue cracking or likelihood of fatigue cracking, which is then reflected in various details. The other factor we talked about was residual stresses. These are the locked-in stresses that occur in a structure. How do they get there? Well, if you've ever been to a steel mill and you see the steel rolling and it's hot, well, it cools unequally, so there's stresses because it cools unequally. The process of welding introduces a lot of residual stresses. Again, they're not bad, they're accounted for, but they're there, as well as other things we do in fabrication, lock stresses in. Primarily what we worry about, though, is weld shrinkage due to cooling. The weld is a liquid metal, it's very, very hot, so it's expanded, if you will, and as it cools and begins to harden, it shrinks and begins to pull material with it. This, of course, then is an uneven cooling. So the first pass of weld is cooled, the next pass on top of it is hot. As it cools, it's restrained by the previous weld and so forth. And so our outer passes are generally in tension. And they can be as high as the yield strength of the steel. Maybe a way to illustrate this is if we looked at a plate that was welded, we kind of think of it as this. It's just simply a plate put together with a weld. But remember, as these weld passes were made, and it wants to shrink, this weld wants to get smaller, it can't because it's restrained by the plates and the previous weld passes. The result is locked-in tensile stresses in the weld itself. Another really powerful way to see this is in the shop. This is a web of a girder with a small flange placed on it. This is probably some kind of diaphragm. And this is what's called a CJP, or complete joint penetration weld. So this is all weld metal in here to join these two plates together. Now, notice this is a nice straight flat plate, perfectly perpendicular to this. But there's a lot of residual stresses here. In order for it to look like this when it's done, the fabricator actually has to do this first. Notice the V bevels. Well, that's so it can be complete penetration. You've had the session on fabrication, and this all gets filled with weld metal. And as that weld metal cools, it actually bends this pre-bent plate back to that condition. This is perfectly acceptable in the shop. The fabricator didn't do anything wrong or try to pull something. But in order to get that, now think about the forces that are locked in here to bend that plate back with just this little weld here. So residual stresses are very, very high, and they certainly then influence fatigue. We'll see how in a second. As I said, they approach the magnitude or the yield strength of the material. The portions we're worried about, of course, are the tensile, because that's how cracks occur in tensile stresses, right? Now that means some of it must be in compression for equilibrium, but we're not generally worried about the compression part. If you've taken a class in stability, though, you do worry about the compression residual stresses, and the column curves have all that included. The worst thing, though, is when our applied stresses, so mechanical stresses, dead load, live load, and residual stresses are both in the same direction and in tensile. And of course, then they add up in a way. Now, we don't specifically add them up, but we worry about their effects in fatigue. So if we go back to our simple illustration of our attachment, remember we knew our live load stresses, some of it gets into the element. So I have tensile stress concentrations from the applied stress. But remember, this weld, as it was placed on each end, wanted to shrink and cool, and that then created additional tensile stresses here. This is very important. Why? Well, let's think about this. If I were to put a strain gauge on the element, or I were even going to make a calculation, but say in the laboratory I'm conducting a fatigue test, and the test is running at plus and minus 5 KSI, cycling back and forth. And I put a strain gauge or I did a calculation, this is the stress I would calculate. But now we know that in that welded detail, there's high tensile residual stresses. So that locked-in effect has the effect of doing what? Well, instead of part of the cycle being compression or minus 5 KSI, and my mean stress being 0, my real mean stress was 15. That's the locked-in stress effect, right? So instead of cycling 5 to minus 5, I'm cycling 20 to plus 10. So I have a full stress range. In other words, the entire stress range cycle is what keeps the fatigue crack growing. And that's explicitly included in the AASHTO specifications, where we require you to check and include a portion of, or the compression portion of the stress range cycle. It's because of the tensile residual stress effects. So, what does that mean when we're all done here? Weld toes are generally what we worry about. I have high geometric stress concentration, so this would be a cover plate, say on a girder. Sometimes you'll look up when you're traveling under an older bridge and you see a cover plate added to add section modulus, and then it terminates abruptly. Well, I see high residual stresses from live load because of the stress, like water, has to come out and get into the base plate. And remember, I have high locked-in residual stresses here. The result, cracking at the termination. That's what we're looking for when we go out and inspect. But again, notice along the length, there's really no stress concentration effects. And so I wouldn't spend time inspecting here. And in fact, the fatigue category along the length is category B, while at the end, it's category E or E prime, because that's where the stress effects are the greatest. So how do we bring all this into the AASHTO specification as users? Well, the first thing is, as you look through the AASHTO code, you'll see that there's different terms, and one of them, of course, is limit states. And we think about limit states as strength quite often, but we want to talk about limit states in general. It simply is a condition beyond which the bridge or the component doesn't satisfy the provisions for which it could be designed. Most typically, we think of strength. It couldn't carry the load. But realistically, we also have to think about other limit states: deflection, serviceability, of course, and fatigue. So the common ones, like we said, are strength and stability. We're more worried about the other one, fatigue, and that's what we're focused on today. But fatigue is a little different. It isn't a single event. It's repeated events. So the fatigue limit state has to include a time factor, if you will. The maximum loading isn't what we're worried about. It isn't the heaviest truck that causes fatigue, say permits in all the lanes. It's rather some effect over time. If you go stand along the interstate, well, off the interstate, I don't want anybody getting arrested or hit, but if you go and watch an interstate, you'll notice that there's trucks, but they're not trucks in every lane every time. It's mostly individual vehicles. And some are loaded and some are unloaded, and some are in one lane and then some are in another. It's a highly variable spectrum like we talked about. That's what we worry about for fatigue. So what AASHTO does is it makes an assumption that, and it's very valid, that we want to have a few number of trucks to design for strength and certainly then for fatigue. And what we call them are notional loads, and that was discussed in one of the earlier presentations. But the point is simply it's a vehicle that is intended to give the same effect as the real trucks, or in our case, the variable amplitude spectrum. A single truck that gives the same fatigue damage, kind of like we talked about earlier. And we want to use one vehicle, right? That makes life very easy, and it's very easy to work with. And if you recall, the fatigue tests in the laboratory are constant amplitude. We apply a single stress range, so it would be nice to use a single truck because then I have a single stress range. But again, it's important. This truck has to give me the same fatigue damage as that entire spectrum of different trucks of different weights and positions. This is commonly referred to as the fatigue truck. It's not often called that in the spec anymore, but that's what, if you say the fatigue truck, people know what we're talking about. And it's based on weigh and motion studies, loadometer surveys from Federal Highway, and field testing. So there's a lot of data behind the development of a truck. And there's an NCHRP report from about 1990, so it's quite old, but it's a good model, that validly developed a truck that represented or produces the same damage in primary elements. And what does this truck look like? Well, as I said earlier, it turned out that the lighter vehicles don't contribute. So the vehicle that's used for fatigue design was never developed using vehicles less than 20 kips, or it was developed only using vehicles 20 kips or greater. And again, that's because the lighter vehicles don't do anything to us in terms of fatigue. Those vehicles are light cars, panel trucks, and what's so. So what does that truck look like? Well, you'll never actually probably see this specific truck on the road, but the basic fatigue truck that was developed years ago is simply the HS-20 vehicle. And if you recall, the H is the tractor, and then the S adds the trailer. So the HS is a tractor trailer, and it's about 3/4 of that, or an HS-15. There's a very important observation here. The HS-15, or the fatigue truck, has a fixed trailer length. Now remember, in strength design, you vary this geometry, right, from anywhere from 14 to 30 feet. And that's because for strength, you're trying to always maximize the effects. What is the worst thing that can happen, even if it only happens once? Well, in the fatigue truck, that's not what we're worried about. What we're worried about is the day in and day out, what happens most of the time type of truck. And that's the long tractor trailer. And this notional load, again, it's not a real truck necessarily, by using these loads and this geometry, we get the same effective fatigue damage as the variable amplitude spectrum. So how do we apply it now that we have some kind of a truck? Well, it kind of depends on the bridge itself and the element that you're looking at. For example, short and medium span bridges, well, fatigue is going to be driven by individual trucks. And you see one primary cycle, because that's important, right? The cycles it produces per truck. This is also very important. In strength design, you would load all conceivable lanes. Not for fatigue. Fatigue, we only load a single truck. And we put it in each lane, but individually to check different locations. That's because it's the day in and day out type loading. There is no lane load either. If you recall from the discussion on loads, you have the truck portion of the load. And then remember there's that distributed lane load in the HL93 strength load. We don't include that portion. It's only the truck itself. Again, it's attempting to be as representative of day in and day out traffic. Now I will caution you, as a designer, if you have reason to believe that the fatigue truck should be in more than one lane, let's say it's a bridge that's going in and out of a quarry, and you know that there's a lot more loading, then you should consider multiple presence. But that's something as a designer you would have to think through and make sure that you need to do that. Now today, as of the 8th edition, we had a ballot last year at AASHTO, the fatigue truck weight, I said it was 0.75. That was the original research that developed that. But there's been additional studies, additional weigh and motion studies, that have looked at the load spectrum in this country. And it's been creeping up, as you can imagine. So instead of 0.75 times the HS20, the vehicle is the HS20 times 0.8. Now you might think, well, that's not a big deal. And it's not a huge difference, but it's just trying to stay current, that things are changing. But there's also something very important here. This is the truck that creates the same effective fatigue damage. This is all trucks combined. Now, when I make that statement, we also have to recognize, though, that means there's going to be a lot of trucks that are much heavier than 0.8 times the HS20, or almost the HS15, right? We know that. How do we address that? Well, we address that through what we call the fatigue limit state load. That's shown that the upper bound vehicle is the HS20. Why do we care? Well, remember, we have this concept of finite life and infinite life. And to ensure I have infinite life, I have to make sure that the stress ranges that the trucks produce stay below the constant amplitude fatigue limit. Remember that horizontal portion of the line. If I assumed that this was my truck for fatigue design for infinite life, I would be wrong for infinite life only. Why? Because I know there's many, many vehicles that are heavier than this. That means if I calculated a stress range and I assumed that that stress range was or I calculated that it was less than a given fatigue limit, and I said, oh, I have infinite life, I'd be wrong because there's a lot of trucks that actually will exceed the fatigue limit, thereby causing fatigue damage. If I want to have infinite life, I have to increase that load to reflect the large number of vehicles that actually are on the interstates that produce stress ranges that would exceed the fatigue limit. So I would use this for infinite life design. I can use the fatigue truck for finite life design, where I'm really concerned about a finite life and the damage accrued. Because remember, it's to give me the same fatigue damage. That'll show up in the next version of the AASHTO specifications. So this idea of finite life, how would I do this? Well, one thing, we have to have some targeted life because it's finite. So I have to decide that up front. That means I need to do pretty good on forecasting, especially in new design. If I want to design for 30 years, I better be pretty certain that I know my truck traffic out that far. I need to calculate a stress range and then the resulting number of cycles, and we would use the 0.8 today times the HS20 to get the effective stress range or the same equivalent damage. I use that with my S-n curve like I showed very early in the presentation. We'll show that again. And I have finite life only useful if my stresses or the number of cycles I produce are less than a certain value. Now that's a tricky mouthful sentence. So let me illustrate this. If I perform finite life, what I'm saying is I would come in at some stress range produced by 0.8 times the fatigue truck and intersect my curve and I calculate the life. And that's perfectly fine. But let me cast it differently. Let's say I said to you, I need to be able to tolerate 10 million cycles. And the detail is category C, this purple curve. Well, what do you notice here? Well, 10 million cycles is out past the point where the fatigue curve becomes horizontal. In other words, there is no finite life that could ever achieve 10 million cycles. So that's why the previous slide says there's limits on where the ADTT can be achieved. Simply this says is if you needed to carry more than 10 million cycles, in this case, or 10 million cycles or more, you have to design for infinite life, or really anywhere in this region. You need to design for infinite life because you've run out of finite life. In the AASHTO specification, we give tables that for each category, what is the ADTT at which you might as well design or have to design for infinite life. If your truck traffic is this high, you'll never be able to achieve finite life. So infinite life is more favorable in a lot of ways. First of all of the cycles are less than the fatigue limit. So it doesn't matter how many I have because infinite of anything is still infinite. So that's nice. The AASHTO approach is to design that so the fatigue limit stress range, remember the 1.75 times the HS20, is below the fatigue limit. The statement then is cracks won't propagate in the life of the structure. And for families of structures referred to as fracture critical, that's certainly the way to go. Now, is this economical? Well, actually it's quite economical because the stresses are linear. So in other words, if I need to lower my stress by 10% or 15% to make it infinite, I simply need to add some more steel, make the girder a little deeper, but it's generally not difficult to improve the fatigue life. And always remember, the other way I can do this is simply use a more fatigue-resistant detail. So rather than have an abrupt termination, maybe I have a smooth termination. And now I have infinite life simply by changing the detail and nothing else. So how does this show up in the specification? Well, we have two load combinations, fatigue 1 and of course then fatigue 2. This is our infinite life combination, and at present in the manual or in the specification, it says it's twice the effective stress range produced by fatigue 2, which is fatigue 2, but with the adjustments in the new load factors, this actually becomes 2.2. So we have fatigue 1 if we're doing infinite life, and then fatigue 2 if we're doing finite life. And basically we get load factors then on the HS20 to allow us to be able to design for both, well, one or the other of those limit states. What about the load distribution? Well, if you remember in the analysis section, there are distribution factors that are used to get the stresses in the girder and the moments in the girders based on how the loads are applied. Now, the load distribution equations in AASHTO are very good, but if you recall, for strength design, it's basically assuming all lanes are loaded. But we said earlier that fatigue is for individual trucks. So if you look at the load distribution equations, they have them for strength, but they also have them for fatigue. And the reason is they've been adjusted to reflect only one lane loading. And that's important so that it recognizes that it's only one truck we're putting on the bridge rather than all lanes loaded. So how do we use the AASHTO fatigue illustration tables or illustrative tables? Well, one important thing is we made some great improvements over the last few years. We used to have these old sketches that were photocopies of photocopies, and that you could hardly read them at times. So they've been all redone and are nice, clean sketches with a lot more information on them. One of the things that they show are these arrows. A double-headed arrow in these sketches represents stress range, cyclic, back and forth if you think of it that way. The welds that we're talking about, and very importantly, these red arrows, or red lines, of where the cracking is we're expecting. So notice for this connection, the stress range is running longitudinal. This is a flange maybe with some attachment on it. Where's the crack shown? Well, growing into the base metal at the termination. Why? Because remember we had the high stress concentrations at the terminations. Now unfortunately AASHTO wouldn't print this in color, so these lines are black in the specification. But they illustrate the direction of the crack. And you'll notice one important thing. This crack is perpendicular to the direction of the stress range, and that will always be the case. The cracking that you're considering would be perpendicular to this stress range because that's how cracks grow in tension. So first thing is when we look at the table, we have to think of the title, and it's called Detail Categories for Load-Induced Fatigue. Well, it is a little confusing, right? If we say load-induced or live load-induced, because you might think, well, it's all live load-induced. Well, that's not really what we're getting at. What the table is getting at by load-induced is it means stress ranges that we calculate. So this is your bending moment in a girder, MC over I, P over A in truss members, whatever, but stresses that we calculate. Nice, simple, nominal stresses. We don't worry about the hot spots, like we said. That's all built into the details. These are stresses we calculate, which then leads to the next question. Well, then what isn't included? What stress ranges do we have that aren't included? And that would be what's referred to as, say, out-of-plane or secondary stresses. We don't calculate these. And so as an example, we design components. We design girders and floor beams and stringers and different components separately. But then we put them together and hope everybody plays nicely. And sometimes that isn't the case, that there's these secondary three-dimensional stress ranges that occur. We don't calculate those. And so those kinds of stress ranges are not what's considered in the table. They're very difficult to calculate, they're complex, and generally we've come up with details that aren't susceptible to this. So today this usually isn't an issue. But it's primary stresses that we calculate. That's what we worry about. The other thing is, always remember, the defects that aren't included, if the girder is cracked already, You can't say, well, it's a worse detail. No, it's cracked. The fatigue categories don't apply. If it's got a lot of damage in it, maybe from an impact from a truck, if there's severe corrosion and whatnot, the categories don't account for them. The details that are tested are assumed to be fabricated to normal quality and the member's in good condition. That's not to say that a little corrosion is going to be a problem, but we're talking severe corrosion wouldn't really be included. Again, if it's cracked, you can't use the fatigue categories. You have to switch to what we talked about earlier, fracture mechanics, remember, which is a way to try to address the effects of cracks in solids. Now there's a table that has a lot of information that we'll take a look at here that has typical bridge details. The challenge by far is trying to map what you have to what's in the cartoons or the illustrations. We have to think about how the stress is oriented. We have to think about what information is given in the tables. Are we doing finite or infinite life design? And where would the cracking be expected? If we can kind of think through those, then we can have a pretty good idea of how to map our detail to what's in the manual. First thing, you have to calculate your live load stress range and how it's oriented in the specific member. So we would run our fatigue truck across the bridge and obtain the stress range. Then we would have to think about the detail. Is it a transverse stiffener? Is it longitudinally loaded, transversely loaded? Is it a bolted joint? But compare the orientation of that detail with respect to that stress range. Then we determine, well, where would the cracking be expected? Is it a weld toe? Is it inside of the weld? Or is it, say, a bolt or rivet hole? And multiple locations may need to be considered on the same detail. If we look at welded details, some of the things that become important are the weld type. In other words, a fillet weld versus a complete joint penetration weld. How is the weld oriented with respect to the stress range? Is it transverse or perpendicular? Does the weld have a weld toe that's visually apparent? I can say that just about all of the time, weld toe cracking is what we worry about when welds are left in place, are not ground away, and we have stress ranges perpendicular to a weld toe. We still have a weld toe if we grind it smooth, like in a complete joint penetration weld of a plate, but it's not as severe as if it's left unground. We still always check the portion that's parallel to the stress range, but it's always going to be better than at the termination. Bolted and riveted joints often are quite a bit easier. The reason is that the stress concentration is round. So we always will have a portion of it perpendicular to the stress range. So that's actually pretty easy when we look at bolted or riveted details. We don't have to think as much. So let's take an example. Say I'm worried about this welded attachment on the side of my girder. My primary stress range that I would calculate due to the fatigue truck is running parallel to this red double arrow, right? So that's my stress range. That's what I worry about. And I'm worried about this attachment causing cracking in that member. Now, it turns out it's a complete joint penetration weld. So, where would I be most concerned about cracking? Well, as we said, stress is like water. So the stress I'm worried about is in the main element, the girder, that's going to come in and come out. So that means I'm going to be worried about cracking at the terminations and at the weld toes specifically of those terminations. How would that cracking be oriented? Well, remember, it's going to be perpendicular to my primary stress range, or in this case, into the main element, perpendicular to the stress range coming out of the weld toes. And in fact, if you were performing inspection, this is where you would have to be. As we step through our table, we find an illustrative example that looks like our attachment. And we would map that to our attachment. We would look at our geometry of our attachment, given that information, and then we can move ahead to be able to pick our detail category, and our information for fatigue. Most of the details are quite easy to find. I will say in this case, this is a category E prime detail, and we don't want to use those. So When we come in and we find the length of our attachment, we said it was about 8 or 9 inches. We know what our thickness was. I'm sorry, it was less than an inch. It was a category E. And we can identify our detail quite easily. Don't use ERE prime details, though. I'm just using this as an example. Those are poor fatigue details, so let's shy away from those. But the easy ones, the common details are easy to find. We thought about stress flow and the detail length, and that's how we were able to find that. There's some good references, and I'm not going to say much about these, but you can look these up. They're for free on some libraries that we've put together to give guidance on how to pick these detail categories and give guidance on selecting yours. So a quick example, if we had a finite life check, what would we do with that once we've determined our fatigue resistance? Given it was a category E, we have a stress range of 5 KSI, and my fatigue limit is 4.5. Well, I need to know how many cycles I have per day. What is the estimated fatigue life of this detail? Well, I simply go into my equations, and I recognize that the applied stress is greater than the fatigue limit. I have a finite fatigue life. I calculate the life using that simple equation from earlier. From the AASHTO table, we got the detail constant of A, and I simply take A and divide it by the stress range. That yields about 8.8 million cycles. But again, that's not too useful for me. I want to turn that into years. So I simply take the number of cycles per day, divide that into the life, and estimate a life of about 13 years or 14 years. How does that look on the fatigue curve? Well, I simply would come in at that stress range, intersect my curve, and if I drew a line down, I'd be at about 8.8 million cycles. For infinite life, these are even easier. Same detail, category C detail, rather different detail with a stress range of 4.9 KSI. This is from my fatigue 1, so this is my infinite life check. I have a lot of trucks per day. What's the fatigue life? Well, I realized that my stress range is less than the fatigue limit. That means all the cycles are less than the fatigue limit because it was from the fatigue 1 load combination, and I have infinite fatigue life, and really there's nothing to do. The detail has infinite fatigue life. And so as we see, we would just keep going out in time because I'm below that fatigue limit. And that's what we really want to do, is design for infinite life when we can. So that's a quick review of some of the fatigue provisions in AASHTO. Hopefully that'll be helpful to you as you begin to try to use those provisions. And we'll just briefly talk about fracture critical. It's a term that's been used for many years. It's an awful term, but it's a term that we have. And it's intended to reflect the concern that a bridge could collapse because of loss of one of these elements. And if a member is called fracture critical, it's fabricated to special requirements in the AASHTO AWS. But the big one is it's then subjected to arm's length inspection every 24 months. And that's one of the laws in the CFRs, Code of Federal Regulations. It came about because of some bridges that had some serious problems built prior to 1970 or so. But it isn't 1970, it's 2017. In fact, we should update this probably to say 2010s. And if we think about how we used to do things versus how we do things now, it's a completely different world. And so the reason I bring this up is we don't want people to be afraid of what we would call non-redundant systems today. The likelihood of fracture is incredibly low. There's been a lot of interest in this because of these advancements that started over 10 years ago. And we're moving quite a ways ahead now to the point where we can confidently say it isn't the 1970s, dude. We are in the modern period where we have incredibly tough steels, wonderful fabrication. We actually design for fatigue now. You probably don't know this, but prior to about 1965, bridges were not even designed for fatigue. Well, then cracking could be expected. There were no toughness requirements like we have today. Analysis was quite rudimentary. Well, today we can do much better on analysis. Non-destructive evaluation or non-destructive testing that wasn't done then that is required today. And of course, fabrication is far more advanced today than it was in the 60s and early 70s. And so the industry is recognizing it's time to revisit this concept that a bridge built with 2 girders can be just as reliable as a bridge built with 4 girders, for example. And so we're doing a lot of work with that here at Purdue and the industry overall. And what we want, especially the younger people on the call, is to start thinking differently about this, that we have what's called an integrated fracture control plan, where this term fracture critical really has no meaning anymore. If you got on an aircraft and the pilot said, "Welcome to our Airbus A320 fracture critical aircraft," you'd probably politely leave the aircraft. But it is fracture critical. If you lose a wing, that's bad. You lose landing gear, that's bad. Why aren't we worried about that? Because it's engineered. And maybe illustrated for structural folks, why don't we have buckling critical members? If you lose a compression member in a truss, that's very bad. But we don't do anything special in inspection for the life of the structure. And that's because we did a lot of research and design and testing, and we can now be confident we don't have buckling is no more likely to happen than any other strength limit state. Today we can do the same for the fracture limit state. And so you're going to see some provisions coming forward hopefully in 2018 that will allow us to exploit this and say it's not the 1960s anymore. The other thing is, no matter what you hear about the term fracture critical, they've performed very, very well. Prior to any fatigue provisions, prior to any fracture control provisions, and believe it or not, prior to when on a two-girder bridge or a truss, when one of the girders completely fractured, the bridges have stayed up. In fact, none have collapsed because of this, even though that's our fear. And there's an NCHRP study you can download for free that talks about this, that all this money we spend on inspection probably wouldn't have made any difference. Incidentally, the United States is the only country that singles these structures out. Europe and in Japan and other countries, they use what's called engineering to treat this concern. We can do the same. So keep in mind that we perform a lot of work doing inspection to be safe, but then we kill someone in a traffic backup. That's not a good thing either. We're more likely to actually hurt someone in a traffic backup because we're closing lanes doing inspections than we are to actually have a crack occur or the bridge collapse. So there's some projects that are wrapping up looking at what's called internal redundancy, where if we take an old riveted member or a new built-up member with multiple components, it's redundant. And projects that are wrapping up looking at complex system analysis, where we model the entire structure and concrete deck and how does that all interact if a component fails. Very interesting work that's going hopefully to be moving forward soon. The outcomes of what we would call an integrated fracture control plan, well, we'll treat fracture like any other limit state, and our probabilities of failure and reliability can be quantified. Treat it like all other limit states. Then that'll allow us to inspect in a rational way and use our resources much more wisely. So what does it mean to those in the room listening today? Well, stay tuned, because the concept of fracture critical is completely going to be overhauled, we believe, in the next year or two, and then it'll roll into hopefully how people design. It'll be an integrated plan where we will link how we inspect, not every 24 months, just because the calendar says it's time to inspect, but the level of inspection, how we inspect, is tied to the design and is tied to what inspectors can find and what the structure can tolerate should you miss that. And we can eliminate these concerns with fracture, and hopefully for the steel industry demonstrate how reliable the structures are overall. And if there's anything to come away with, is that it isn't the 60s, 50s, 70s. We don't build those bridges anymore. And so the modern steel bridges shouldn't be treated that same way. So I guess a quick summary. Fatigue, remember, is slow and stable. You can inspect for that. It drives slow. If I take the load away, cracking will stop. We had detail categories, right? We had numbers of trucks that drives that, and the stress range. This is the load side. How big is the stress range? How many times? This is the resistance side of the equation. If I can keep my stresses below the fatigue limit, well, everything's okay and I would not have damage. But if I do have high enough stress ranges, I can simply calculate the life with this simple relationship. Fracture, on the other hand, though, is slow and fast rather, and unstable. And so it can be driven by live load, or is driven by live load and dead load, as well as the material, the applied stress, and the cracks that could be present. And even if the load goes away, we could still have a fracture if the temperature would drop because of its influence on material. Remember, we talked about the load side, the fatigue truck as well. That's a notional truck, not a real truck, but it's trying to give us the same fatigue damage that the variable amplitude spectrum does, all wrapped into one truck, easy to use for design and evaluation. A difference of the how it's used in strength, right? Remember in strength you cycle through 14 to 30 foot trailer spacing where we hold it constant at 30 feet, and it's based on real weigh and motion data, so we can have confidence that it's based on real information. And I apologize, you might want to note on your slides, this should say 0.8 and 1.75 for the next version of AASHTO. But today this is what you would probably see if you opened up the specification, is the old 0.75 and 1.5. But this will become 0.8 and that will become 1.75. And so with that, I believe, oh, we have some questions. So Christina, you're going to handle these, is that right?
Yes, I'll take care of that. Thank you very much, Rob. And before we get to audience questions, we have a couple of quiz questions here. I'll read those to you. Here's the first question. What factors influence fatigue life? Choose all answers that apply. Stress range, number of applied cycles, compressive strength, dead load, tensile strength, detail category, or yield strength. What factors influence fatigue life? And choose all that apply. Hint, there is more than one correct answer. You can go ahead and select your answer on the screen and click on Submit. Okay, we have just about everyone that's answered. So Rob, it looks like most people have chosen stress range, number of applied cycles, and detail category.
That's excellent.
We have a few people that selected tensile strength. Maybe about 20% of people out there selected tensile strength. Could you tell us why that's not correct?
So in our structures, tensile strength in fabricated steel bridges, tensile strength really has no influence on fatigue life. If you had polished steel and you had different strength steels, tensile strength would make a difference. But the difference, that influence is very, very small as soon as you would weld the steel or cut a notch in it or drill a hole in it. The effects of how we fabricate effectively erase any of the improvements you would see by improving the strength of the steel. Higher strength steels that would be polished would exhibit a higher fatigue resistance generally. But as soon as we fabricate them, all that goes away. So because we don't polish our bridges and stress relieve them and get rid of the residual stresses or the minor defects from welding, any of those other little benefits are just hidden away. And it's stress range, the number of cycles, and the detail itself that drive that.
Okay,
and that's the same
great.
for yield strength as well.
Okay, and I'll move on to the next question. True or false? The AASHTO fatigue categories can be used in cases where cracks exist as long as they are pretty small. True or false? The AASHTO fatigue categories can be used in cases where cracks exist as long as they are pretty small. Okay, it looks like we have just about everyone has selected their choice. Overwhelmingly, we have the audience is saying false.
Okay, so the audience is correct. The answer is false. Now, I can see maybe where some people put true. The small little defects that are present from fabrication, or maybe the little bit of cracking that you could get in a test, but that's not what we're talking about. When we say small, we mean that you could even find. The type of cracks that could be present, say, from fabrication are basically not even detectable by, say, magnetic particle testing, certainly not visually. So the correct answer to this is if there's cracking present, you cannot use the AASHTO categories.
Okay, great. And now it's time for audience questions. If you have not yet sent in your question, you can go ahead. You can still do that. Just send it through the chat. And our first question, I will take us to slide 15. I think this is where it first came up. Could you remind us, what does CAFL stand for?
Sure. It is constant amplitude fatigue limit. And so that simply is saying that if my fatigue stresses let me grab my pointer back. If my fatigue stresses are below that value, so down here, I would be expected to have infinite life in my detail.
Okay, and a question about infinite life. So why would you not always want to design for infinite life?
That's a great question. In my opinion, you should. If you think about that a bridge structure is going to be probably out there for 75 years, if we think we can forecast what kind of loads and number of cycles it might have, so generally you should design for infinite life. But there are cases where it could be prohibitive, where you would say, well, I'm going to design for finite life, maybe on a temporary structure, for example. Sometimes you have to put a temporary bridge in, right? It's going to be there for a certain amount of time. Well, maybe in that case you would design for finite life because it's not going to be there for more than 3 years. But generally speaking, I would encourage folks to design for infinite life. And it's generally easily attainable.
Okay, great. All right, the next question, is there any difference in terms of fatigue life among the following 3 different scenarios? So although they have the same stress range of 10 KSI, the first scenario would be 2 KSI to 12 KSI compression. The second scenario would be 6 KSI compression to 4 KSI tension. And the third scenario would be 2 KSI tension to 12 KSI tension.
Sure. So generally speaking, the answer would be no. And that has to do with the residual stresses. So let's take in a welded detail, because I know my answer will apply to that. At a weld toe, the residual tensile stress that could be, we generally accept as present, is on the order of the yield strength of the steel. So that means that the locked-in tension at that weld toe is, say, 50 KSI in tension. Let's just say it was at yield. That means the most compressed one there, -2 to -12, I think it was, it's, that if you calculate it, it's negative, but in reality, it's actually much higher than that at the weld toe. The only thing is that in AASHTO there is one provision that allows you to ignore fatigue if the compression dead load stresses exceed the stress range from the fatigue limit state load. And what that effectively says, so in other words, the compression, say the compression stress is -10, the fatigue limit state load cannot exceed a stress range of +10, or plus, say, 9. It has to always be more. In other words, it can never go into tension even with the fatigue limit state truck. There is a provision in there to allow you to do that. Now, it could still crack. And I can tell you, when we do fatigue tests here in the laboratory, they're all generally simple span girders. And the students always go out and look at the bottom flange. That's the tension flange. And I tell them, and look at the top compression flange. And they say, why? Because of the tension residual stresses. And sure enough, we crack compression flanges. Why is that? Because of the high tensile residual stresses. They're actually cycling in tension due to the residuals. The difference is the bottom flange will eventually break in half because everything's in tension. The top flange will crack, and then it stops. It enters a compression residual stress zone. But the basic question is we would not treat them any different in AASHTO unless the dead load stress, unless the live load stress range is always hidden by the compressive stress.
Okay, great. Thank you. For our next question, I'll take us to slide 79, where we have this cover plate. Would rounding or tapering the end of the cover plate upgrade the fatigue category for the square end termination of the cover plate?
Another great question. So the research that was done on these back by John Fisher in the mid to late 1970s, even into the 80s, showed that there was really no difference in what you do at the end of the cover plate. In fact, even that end weld where the 2 little arrows are in the presentation, even if you eliminate this weld, it doesn't really make a difference. Now, there were slight improvements, and you can find that report from Lehigh, but it wasn't enough. When you remember there was a lot of scatter in the data, there wasn't enough to say that if I rounded these edges or if I made them square or I taper it, that it was enough to worry about. And the real reason is this red spot, right? You always have that kind of no matter what you do here. So no, there isn't really a big difference in any of the details.
Okay, great. Thank you. Okay, I have a question that might be a little bit off topic. If you can answer it, great. Are the ways that DOTs count trucks as a percentage of the average daily traffic representative of what should be done?
That's a good one. I would have to say yes, only because I rely on them to give me the average daily truck traffic, right? So that's usually how they report it for convenience, as a percentage of the daily traffic. The thing you really want to make sure of when you get the ADTT numbers, no matter how they got them, is what are they giving you? I've learned over the years that traffic people tell you 1,000. The truck traffic's 1,000, and then you find out that that was for both directions. So it's 500 one way and 500 another, and you have two twin interstate bridges. Oh, well, now I'm off. And what we also use, and this is in AASHTO, is what's called single lane ADTT. In other words, what is it in that one lane? Because remember, the fatigue truck is assumed to be one truck in one lane. If the ADTT is spread across lanes, like 30% in one lane and 70 is in another, you need to take that into account. So rather than having the actual ADTT number, how they give it to you, it's more important to know, is it bidirectional and is it per lane, and that kind of information when you're doing an evaluation. I will say, without a doubt, the best way to do any fatigue evaluation, if you're running into problems with life calculations on existing bridges, is pay the little bit of money to put a few strain gauges on the bridge and let the bridge tell you what its remaining fatigue life is. Because generally our estimates are quite conservative.
Okay, great. And it looks like we have one last question. Also might be a little out of the scope of your presentation, but I'll give it to you and you can give it a shot. What about using Paris's law for predicting fatigue life?
Yeah, there's nothing wrong with doing that. When you do that, of course, then there's no variability, right? You'd have to be careful when you do that, because the fatigue curves that we use include the effects of defects from welding, residual stresses, all those things. Paris law, if you ran the number 10 times, you get the same answer. If I do 10 fatigue tests, I get 10 different answers, right? So somewhere you'd want to put a factor of safety in that, I guess is what I'm getting at. And the other thing, for Paris law to work, you need an initial crack size. Fracture mechanics, that's what that's based on, has to have an initial crack size. And if you've run those numbers, I assume the person has, you can find that the life you get is incredibly sensitive to the initial crack size. So you just need to make some good assumptions and use good engineering practices if you want to use that. But we do that all the time. Where that comes in useful is if you already have a crack and you want to rough out how long do I think that could stay there before it becomes unstable. And that's a whole other discussion on what's called fitness for service, but that's done routinely.
Okay, great. Looks like we have one more that came in. Let's just try to squeeze this one in. If an element is fabricated with a very small crack, can you still develop a constant amplitude fatigue threshold by testing?
If it has a crack in it, technically you could. You'd have to use fracture mechanics to begin to try to infer what that was. So if it had a defect in it, say you knew it had an 1/8 inch crack, you could keep your stress ranges below the what's called the material. I can't think of the term what it is now, but it's a material property of when the crack would be expected to grow. And so when we do fracture mechanics checks, when we do fitness for service, we're doing a project for NCHRP, and that's how we're doing it, is we're assuming that there's an initial defect of a certain size. How large can it be before it would be expected to grow, or how big can it be and not grow for a given stress range? Again, there's some assumptions in there that you have to be careful with, but that's using a fracture mechanics approach.
Okay, great. And that's all the time we have for questions today.